A great asset of constant programming is the flexibility that you have to implement a non-deterministic search. So by default here, I used first fail search as a strategy to guide the search when I'm exploring my branch and bound search tree, my depth first search tree. I would like to show you what is implemented here behind the scene for you. So when you have to implement the search, you have to think recursively. So the situation is the following. You are exploring a search tree like this one, a binary search tree. And at a given moment, you are, for instance, in this node. In this node, the state of the current domains is represented here. You can see that I have all the domains here and all the possible values left. And what I would like to decide is which variable I should branch next and which value I should try on the left and remove on the right. So what I would like to do is continue this search tree like this by creating two different branches. One would decide that a variable should take the value v on the left branch, and on the right branch, I will decide that the same variable will remove the value v. Okay, so this is what I would like to do. Now the question is, which variable should I pick and which value should I decide? This is the goal of the branching scheme. And a good strategy for that is first that you should, of course, not decide a variable that is already fixed to a given value. So for instance, in this case, I can forget queen 4 and queen 5 because they are already decided. And a good strategy is to take the one that has the smallest domain that is not yet decided. And so probably the one that I will pick is this one, queen 1, because it has only two values left. Okay, let's do that. So I will replace my branching scheme. So let's comment it instead. Okay, to make sure that I have exactly the same behavior after. I will replace this and I will implement a callback procedure, so a closure, to decide to implement the branching scheme. So I do it like this. Okay. And then I need to decide which variable I should take. And I have here in branching scheme something that is called select min, which is very useful for that. I give the array of variables. Then I have a first predicate that will filter the variables. And so I will filter out all the queens I take only the ones that have a domain size that are larger than 1. So like this. And I will select the one which has the smallest possible size. Like this. Okay, and I select this variable and I call it the variable x. Okay. So probably I should call it differently, like this. Otherwise, Java will complain. Okay, this works. Once I have this, I should decide which value I take. So I will take, for instance, the minimum of the domain. So in that case, that would be the value 1 here. I take the minimum and I put it inside V. I take the minimum of the domain. And then I will return two branches. Okay. And branches are again procedures that will post dynamically a constraint on the left and another constraint on the right. And so in this case, that will be I take x and I say it should be equal to v on the left. And on the right, that would be something different. We go to the next slide. And I will remove this value, this same value v, from the domain. Okay, this will work. Okay, but I need to deal with a special case where all the variables are already decided, and in that case I should say that I have nothing to do. This is a leaf node of my search tree. And so I can test this easily like this. If x is null, okay, which means that the predicate cannot select any variable here because all the variables have a domain size equal to 1, for instance. So in that case, I retrieve a variable that is null. I simply return empty, which is a special constant to tell the search that this is a leaf node. And I should return it. And that's it. So you see, this is how we implement the first fail using minicp. I can run this. And you see that I have exactly the same solutions, the same set of solutions as if I would have used this instead. But now I have a complete control on the branching decision that I need to take in every node, single node of my search tree. And so this is very flexible, and of course this can have a huge impact on the efficiency of the search. And if you want to measure the efficiency, a good strategy is to look at the number of choices and the number of fails. Of course, the number of solutions should not change. But if you see that by selecting the smallest domain size, instead of taking the smallest domain size, I take the largest domain size, probably I will have something different. Sorry, it was not this. This is the filter, so this one. And you see that it has increased the size of the search tree. So it's always a good strategy to select first the variable with the smallest domain size, like this.